Okay, in this video I'm going to talk about post-processing results. And in the previous video I modeled a composite beam, and the video went long, and I decided to stop it and record this video, which is about how to read the results and how to interpret the results. Okay, so if you remember, the model I had was, we had a cantilever beam. On left side I had a clamp, the left side, and then on the right side I applied a force in X direction. The force was equal to 300 Newton. The width of the beam was 10, the height or thickness was 3, so it was 30 meters squared. The cross-section area was 30 millimeters squared. This is equivalent to 10 megapascal of stress on this face. So if this was like made of isotropic material like a steel, I was gonna see normal stress in X direction equal to 10 megapascal across the beam. Okay, so when we made the composite beam, if you remember, we used plies with certain direction, fiber direction. The top layer, it was made of glass epoxy. Top layer was 60 degrees. The bottom layer was, the mid layer was 0 degree, and then the bottom layer was 60 degrees again. And I showed you guys that with this orientation, the material will be like quasi-tropic, and as you see, it deforms like in axial direction, goes like a straight. For other random orientations that I showed in my previous video, you saw that the beam deflected like in not in axial direction, depending on the orientation. If you remember, we had a case that this was like had the transverse deformation, but this one is going straight. Alright, so let's say after you do this analysis, we want to see the stresses layer by layer and see how they make sense. So let me delete what I have generated before so that I can remake them again. Alright, so that you guys can see the process. Alright, so this is my beam, and I want to make normal, I want to see normal stresses in one of my layers. So when you select normal stress, then the software is gonna ask us what ply we are interested in seeing our stresses. So I can go here up and select the top layer, and then once I hit apply, then top layer is selected. If you go down, you guys see that here it says that it is, you can here determine or select the coordinate system you are interested in seeing your result. We have a global coordinate system, as you see here, and we have a fiber coordinate system. Fiber coordinate system is along your fibers. X coordinate in fiber coordinate system is along x-axis. X-axis in fiber coordinate system actually is your longitudinal direction, and then y-axis is going to be transverse direction. For now, I want to see just based on stress normal stress in x direction based on my global coordinate system. Alright, so if you rename this top line, normal stress in top line, and then we evaluate the results, I'm gonna see my stress in my top layer in x direction. Alright. Okay. So by probing, you guys can see how much the stress is. You see it's quite consistent, and along x direction, I can zoom on that region. See here I have edge effects. I mean, this is where I am applying my load. So let's look at the stresses here. And this face is close to 10 megapascal because this is the point of action of my load. But as you go farther, you guys saw that as you got farther, you guys saw the stress becomes 4.8 megapascal. Okay. Alright, so this is what my top layer is carrying. If you want to look at the stresses in y direction, you can do that too. It's not going to be substantial, and you see that's actually almost zero. I have some stresses. The max happens at the boundary condition here. The stresses at boundary condition and left fixed support is gonna heavily depend on the way you are modeling that corner. So for this analysis, I'm not interested in actually seeing stresses close to boundary conditions. I'm just interested in the middle of the beam. This is where our equations that we are developing in our course is gonna be actually are gonna work just similar to 309. They assume that our where we are finding stresses are far from edges, because again Saint-Venant principle holds here too. Okay, so this is what you see in the x direction. Again, let me show x direction again. I have stress of in x direction almost 5. You guys saw that in the middle was almost 5, 4.8. So this means what? This means that you remember the thickness of the 3 layers was 3 millimeter. Each layer was 1 millimeter, and the width was 10. So 4.8 megapascal of a stress means that if you the total force applied to this edge was 300. 4.8 and 5 times my area, which is like 10, means that 48 Newton of that 300 force is carried by the top layer, the next direction. So 4.8 times 10. And let's see how much force is carried by the mid layer and also the bottom layer. So so far we know that 48 Newton of it is carried by the top layer. Before doing any analysis, I know that my mid layer is gonna carry more load because it had fibers along x-axis. So I will not be surprised to see actually more forces or more load is carried by that layer. So let me call this normal stress mid-ply. Alright, so again, ignoring the effects on edges, I don't care about those. Let's click at the middle of the beam. You guys see that my normal stresses are 20 point, is quite consistent, is 20.3. So 20.3 is my megapascal, is my stresses, times 10 means that 203 Newton of that force is carried by the mid layer. And so the mid layer, as we expected, is carrying more load because it had we are not surprised because it has fibers along x-axis. Alright, so let's look at our stresses here. You see is 14 is like closer to 10. We are applying on average 10 megapascal of stress on this end face. Alright, but the load sharing occurs here, so each ply is going to take their own share of load. Since mid layer has fibers in x direction, it's going to take more load. Alright, so you can look at y, not y. Y is the thickness. You can look at the stresses in z direction, which is along the width. You can click here, see how much it's tiny. So in along the width and along the thickness, you can look at the stresses too. Let's see what we get. Alright, so let me see. Okay, again, it's not significant. Okay, so let's look at the last layer, stresses and normal stresses in my third ply, the bottom ply. And let's see. Okay, I have to select this and then select this and then apply. And let's look at the coordinate system. Is again fiber coordinate system. I have to change it to global. Right now I'm looking at the global coordinate system. Okay, so stresses in x direction again is close to what we had for the top layer. For the top layer we had something similar, 4.85. I have here 4.853. Okay, and then mid layer we had, sorry, I've changed the mid layer to, it says fiber coordinates. Actually for the mid layer, since the fibers are along x-axis, for the mid layer fiber coordinate and global coordinate are on x direction, are going to be the same. Alright, so for the mid layer I have stress of 20. Alright, so again 20 means 20.3 means that 203 Newton is carried by the mid layer, and the top layer was carrying 48 and the lower one 48 too. Those two add up to 96, actually 97, and then added to 203 here, I'm gonna get 300, which is my total load in x direction, which is what the force I applied to this face. So we have equilibrium, so we had a force 300 here. Okay, so this is stresses in X direction based on global coordinate system. So what happens if I'm interested in sigma L and sigma T, which is actually most of the time these are the stresses I'm interested in, sigma L and sigma, because failures happens in principal directions, and failure theories are defined based on principal directions, similar to isotropic material. So the top layer, I'm going to change it to fiber coordinate system and sigma X. Let's see how much I get for sigma X. And the stresses here are, you see it's not significant, 1.2. And if you want to see the stresses in transverse direction, which is my Z, based on the fiber coordinate system, my stresses are going to be 3.46, and in other transverse direction, let me see how much my stresses are going to be. It's tiny, so this is a line thickness. So line thickness, which is my Z, the stresses are negligible, but in transverse and in longitudinal direction we had some load, but still it was small for top layer. Alright, so let's go to mid layer. Mid layer, actually, what I see in global coordinate system in X direction and the fiber coordinate system in X direction, they're going to be the same. So I said that already, but let's show you that. So fiber coordinate system in X direction, you guys see that I'm going to get same thing, right? It's not surprising. And so the mid layer is going to carry the highest load and highest stresses. So for this structure, if this is going to fail, it's going to fail. The mid layer is going to fail first because it's carrying the highest stresses, high loads. Right? So let's look at the transverse direction. That one is not large. Technically, we shouldn't see, if we had just this ply and we had force in X direction, we shouldn't see any transverse stress. The reason we are seeing this is because this composite, we have the top layer and the bottom layer too. So, and they were not in X direction, the fiber. So that's why you observe this stress. Okay. So this was the mid layer, and the bottom layer, again, let's look at transverse, longitudinal on transverse stresses. Let's look at that. And okay, stresses, you can see this is longitudinal and transverse. For this one, the coordinate, let me see, the coordinate is fiber coordinate. Yeah, so for this one, actually, transverse stresses are larger. Right, so let me see the top layer again. Transverse stresses in y direction, let me see, how much was it? Yeah, as I said, the mid layer is going to be the key. Okay, so yeah, these are the same. The top layer and the bottom layer, the stresses are the same. Okay, because of symmetry, it's not surprising. So, alright, so as I said, the fiber coordinate system is more important because It's gonna give me sigma L and sigma T, and if you're interested in shear stress on as well, tau LT, you can see that too. So you come here if you want to see tau LT, and then come here, and I'm gonna select the midsection. Okay, the midsection. Go down. Yeah, fiber coordinate system. So let's see how much is my tau LT. Again, here. It's 0.3. It's not significant. Tau LT is not significant, and it's quite uniform. I mean, the first failure theory we are going to study for a lamina is maximum normal stress. Maximum stress theory. It's not just normal. So based on this theory, the lamina fails if your sigma L, sigma T, or tau LT reach their ultimate values. So this theory is the most basic one, and you see that it doesn't consider the combination of these stresses. It just says whenever sigma L reaches sigma L reaches sigma LU, which is something we studied in chapter 3. So in chapter 3 we learned how to find maximum normal stress in longitudinal direction, and in transverse direction also we studied that. And tau LT U also is something we can find. So this theory says once any of these guys reaches their ultimate values, we have failure. So you see that applying this theory is easy. So for this example I had, if you look at the mid layer, was the most critical one. You come here and then you look at, based on fiber coordinate system, you look at your maximum sigma LT. Sigma L, your maximum stress in longitudinal direction. This is 20 megapascal. If this is less than the strength of your lamina, then we don't have failure. If it exceeds that, we have failure. And you do the same for you do this the same for y direction, and then you find it, right? So y direction or transverse direction, this is my stress, and then you can see tau LT here, which is what I found for you guys. Alright, so if all these stresses are less than my ultimate values, we don't have failure. Alright, so I hope you guys find this video useful. I thought it's a good idea for me to show you guys how we can actually, once you have the results, how we can come back and analyze our results, see how whether they make sense or not, and how we can actually analyze failure. I know ANSYS does also failure analysis. You can define a criteria and see if whether it fails or not, but for us, for now, I think looking at the concept is more important. So this course is not about teaching ANSYS. I thought ANSYS can help us to understand the concepts better. So that's the reason I'm using it here. Alright, I hope you guys find this video useful.